All right, so my name is Philip Zucker, and today I'm going to sort of talk about just sort of a smorgasbord of things I've kind of been thinking about, working on, or blog posting about over maybe the last year or two. I like code. Like like when something's in code, like it feels more real to me. Like people have different criteria of like what makes something make sense to them. And when something's in code, I feel like it really makes a lot of sense to me. And I've gotten pretty used to code. So, I like it. And also, different ways of looking at things really change how you think about them. And language significantly influences thought. Like if you're used to mathematical notation or the mathematical style of doing things, you're going to think about things in a really different way than a person who's a programmer or someone who's doing code. And likewise, even in the subclass of people who are doing code, like which particular programming language can also really change how you're thinking about things. So I've been sort of exploring different ways of looking at categories and ways of thinking about how to encode categories into computers. So here's sort of a survey of sort of some of the styles that I've come across. I think it's, I'm into programming languages, so I kind of just want to talk about programming languages because it's fun. But B, it's interesting because I feel like at different stages, I felt very mentally constrained by particular styles. They make me think about things in particular ways. Certain things seem really hard, certain things seem really easy. And by seeing sort of the spectrum of what's available, it widens my perspective, and I can think about different ways of going about things. It'd be very difficult. So my starting point is Haskell. Like that's sort of where I cut my teeth in category, like the connection of category theory to computers. So in Haskell, there's this standard type class that's in base category. And basically categories are types that have sort of two type slots in them. Anything that fits this type class is a category that has these two operations, identity and composition. And sort of here's the pattern here that morphisms are types with two type parameters. That's sort of this thing you get into your head. And then objects are types. And the reason it's interesting is because composition is well typed. When you do this, you actually can't make a ill-formed composition that the Haskell type system accepts. Also, something that's pretty cool is that unification and type inference can do a lot of work for you. The type class mechanism can sort of fill in stuff, and also it can infer usually, like when you apply an identity somewhere, like it figures out what this A is, which is pretty nice. A reason that category theory has such a mind share in Haskell is because it's actually really useful and interesting model of polymorphism. So there's some pretty crazy tricks and encodings you can do with polymorphism in Haskell that maybe it's hard to think about, and it gives you a model of them. And it also inspires new constructs that you can use in Haskell. So it sort of goes both ways there. And you can find more about that sort of thing in like Bartosz Milewski's Category Theory for Programmers course, or looking at Ed Kmet's libraries and things like that. So this is really great stuff. I mean, the reason I sort of got into this is because I think all of this is so cool. But it does, when you start to try and do it, this works like really well when you're talking about Haskell functions as a category. But at certain points, you want to do like different categories, and sort of the objects become like not just any type, or you want to do something sort of interesting. In particular, the objects are interesting. In that case, you end up having to do like wacky sort of type level programming. And I think since this is the thing I saw, and this is the thing everybody was talking about, at some point I sort of equated this type class or the idea of like a type with two slots in it being a category in some sense. But I mean, a category is a mathematical concept that has an intuition to it. And this is no more a category than this is the natural numbers. Like the natural numbers are this intuitive thing that we understand, but this is sort of like one particular formalization and slicing of them. So it's been really fun to like see other styles. One thing I really want to highlight is the compiling to categories work by Conal Elliott, which I think is fantastic. Like I'm a big fan of his work. So if you haven't seen that one, I highly recommend it. So then highly related to this is category theories in theorem provers. And this is a big area because people who like category theory are very mathematically minded. And some people who are doing category theory just kind of want to do proofs about categories or use categories as a way to frame other proofs. And often, at very least in the sort of dependently typed languages like Agda and Idris and Coq, it still kind of looks pretty similar to this, what they're doing. But then they're allowed to have dependent types. So it's not per se that this parameter is a type. Now it can be a value there. And here's some example libraries. Here's an interesting math overflow that just has like a list of all sorts of different formalizations of category theory. Even in this thing, they aren't all of this style, I don't think, because not everything is dependently typed. So I assume that other things may encode things, other formalizations may encode things differently. But I sort of think of this particular community, this categorical cybernetics community, trying to take the shift of focus away from these proofs, these formalizations. Because it's sort of a saturated market. I don't know about saturated, but there's a lot of people working on it. And there is a wider spectrum of applications of category theory than just using it for proofs. And a book that really opened my eyes to this is this computational category theory book. So this is from the 80s, I believe. It's Burstall and Reidherd. And in it, they use ML, and they don't encode it in anything that particularly looks like this. They encode it more so that everything is kind of at the value level, which is easier. You don't have to be, you're not mixing up confusion of like dependent types are really complicated and confusing, or theorem provers are really complicated and confusing. It's just like data, the category can just be a bunch of data that you're manipulating like you'd manipulate anything. And so there's a lot of really interesting stuff in there, and that, it's an interesting book. So two other popular languages that I think make sense for a different style of category theory than is per se prevalent in these two arenas are Python and Julia. I mean, there are other programming languages, of course, but I think these are two predominant ones that make sense. If you want to do computational category theory, where you're like trying to compute, you're actually trying to calculate things, instead of just proving, you're calculating. Python makes a lot of sense. It's ubiquitous. A lot of people know how to use it. It has a lot of packages. It's really popular. And I spent some time exploring how to do things there. At the moment, though, it's not where my primary interest lies. And sort of the thing I'm pushing more towards is using Julia. So basically, CatLab is the thing that brought me to Julia. I didn't know Julia at the beginning of the year, and I've been making a concerted effort to try and learn it. And at first, I kind of hated it, but I've actually come to really enjoy it. And there's a lot of interesting stuff there. So things that Julia has going for it is it's still an acceptable syntax for scientists and engineers. This stuff is pretty close to a no-go. It's just, I mean, if you have to become an expert in your domain and also dependent types or something, like it's a really rare person that can do that. Julia also has a really fascinating package ecosystem. Like Python has lots and lots and lots of packages, but Julia has some really unique packages that do really fascinating stuff. That's actually, besides, I mean, CatLab you might say is part of that, but that plus the packages that are in Julia have interested me longer than learning Julia itself has. It does have a fun set of features. You can actually implement novel algorithms fast, which is not so much true for Python. Open-minded experimental community, and there's a link to CatLab. All right, so this notebook, I'm going to go through some examples, and I did do them in Julia or pseudo Julia. It ended up being a lot of work to try and get things actually right. So I gave it a good try. So just to get us started, sort of what do computer functions as a category is sort of one of the first things people talk about when they're talking about category theories on a computer, and it's really the inspiration for this one in Haskell. And so what does that look like in Julia? So you can make a bunch of structural combinators that tell you that this category is at least informally a Cartesian category, Cartesian closed probably, although I've suppressed any closedness. Basically, I'm sticking to Cartesian for the talk. So you have a bunch of base structural combinators, and you might have some domain-specific atom morphisms that you want to mix in there. So the identity morphism looks like that. Takes x any x to another x. Composition is regular function composition. O times sort of does things in parallel. That's the monoidal product. You can copy things. You can extract the first thing out of a tuple, second thing out of a tuple. I think this is supposed to be not that interesting, probably, to most people. Oh well. Okay, so this I designed sort of in the style of sort of what you would see in Haskell, but now I'm going to sort of take us a little bit closer to what I think of as the CatLab style. I did not make CatLab, so I'm putting words into their mouth. I'm putting words in my mouth that I think are kind of words they might say. So you don't necessarily. So there's a constant question in category theory or in mathematics of whether you want to use like strict equality or isomorphism for things. So like here, like this tuple, this associated tuple, it's isomorphic to this other tuple. And maybe you don't want to focus on that. Maybe it's kind of a pain to have to like manually do these associations all the time. So maybe it's convenient to have these two things equal on the nose. And so one way you can do that is a flat representation. Instead of tuples, everything could just be arrays of values. And yeah, arrays of values. So you're flattening all the tuple structure. Everything's associative on the nose. You're getting rid of some pointer indirections, which might be nice. But then when you actually start to go to do it, you see that you can't, okay, identity is fine, compose is fine. But first, how do you deal with first? Here, you sort of knew you have the two pieces sort of already separated out. I mean, but now it's not clear like which sector of the array you want. So there really isn't any magic here. You need to just somehow have the data around that you need to figure out what you need to do in these cases. And there's some options. And what Haskell and stuff sort of do is they sort of encode this information in types, or that they might be inclined to do such a thing. You can also just user annotate everything. Like you can't figure out what you need. We'll just throw another parameter into this function. It's the user's responsibility. But another option is sort of have wrapper types that sort of carry around the little bits of extra information. And that is closer to sort of the CatLab style. And what you get on top of that is then you get to use the Julia overloading, where it selects which version of identity and first and compose depending on these types or sort of incoming. So that gives you something that's it gives you a ad hoc polymorphism. It gives you overloading analogous to type classes might give you, or classes might give you in another language. So in here, I can wrap stuff up in a fun morph structure that carries around explicitly a domain and codomain. And then I have an object structure. And then you just need to like give the right parameters to figure out like which sections of the array to extract. So you need to give first the two objects that it's sort of acting on, the tuple of objects it's acting on. And from that information, you can figure out. And then it can also fill in the domain and codomain for later usage. So that's a whirlwind through that one. All right. So that's functions as a category in 5 minutes. Now let's talk about another interesting category, which is another primary category to like develop intuitions of things and is very familiar as a programmer, and that's Finvect. So it's basically matrices. It's linear operators of the morphisms, and objects are vector spaces. And so how can we actually represent that in Julia? Well, you can represent linear operators by the matrices, and you can represent vector spaces by just an integer of the dimension they're going from and to. So it's, the vector spaces are represented by integers, which is kind of an interesting way of going about it. Now, something to note here is that this is data. Unlike functions, something that's functions are incredibly powerful. I'm a big fan of functional programming, but they're powerful. It's sort of the power cuts both ways, and that they can do all sorts of things, but then you can never really introspect into them. They're a thing that presents a single interface that it can be applied, typically anyway. And so you can't look inside it. But here we're representing a morphism as pure data. And so it really opens up the possibilities of sort of things you can ask and things you can do. OK, so here's how you can implement some of those same structural combinators in this new category. The identity morphism is an identity matrix. Composition is matrix multiplication. There are at least 2 monoidal products, but the monoidal products I'm going to focus on is the direct sum. And basically, you stack 2 matrices along the diagonal, and that makes a matrix that sort of operates in parallel on 2 vector spaces. You can copy a vector by stacking 2 identity matrices on top of each other. You can extract the first hunk of a vector space by having an identity matrix horizontally stacked with a 0 matrix, and similarly for the second, and so on. And then you can also have sort of more domain-specific. You're going to want some domain-specific matrices if you're actually doing anything. And so here's them actually written out. The identity matrix on the 2 object, on the 2-dimensional vector space, is a 2x2 matrix. This is what first looks like when you lay it out. Here's what copy looks like when you lay it out. I'm taking the pair of a first and second, which should be equivalent to the identity by categorical reasoning. And in fact, it is the identity matrix. So, it's kind of cool. Now, that's not the only choice. That is a very natural choice for representing linear operators, but it's not the only choice. There's actually another choice that can be very useful and powerful, and that is the functional representation. Now, again, as I said, the downside is you can't look at things. So that kills some of the operations you might want. Gaussian elimination is going to be very difficult, for example, or lots of linear algebraic questions you might ask are going to be difficult. The one thing it's good at is multiplying a matrix times a vector. So you can, you represent a linear map as a function that takes a vector to another vector. And then by convention, it just so happens to be linear. But you can also go back and forth between this representation, this representation. You can build a function out of any matrix by using the matrix multiply operation. You can partially apply that, and that'll make a functional representation. And vice versa, you can reconstitute a matrix by applying the functional representation to a complete basis. But this is very inefficient. And this isn't a novel idea. There's a Julia package for it. You'll even find it in SciPy. This isn't crazy. And it's actually a useful concept to consider representing linear operators as functions, because you can mix and match different representations that might have very efficient ways of applying themselves to vectors. So you can mix and match a sparse matrix with a dense matrix. A canonical example where this is useful is the discrete Fourier transform, where there's the fast Fourier transform algorithm, which you can reify into a matrix. The DFT is a matrix, but the correct way of doing it basically is an algorithm. And so it's a function. And then you can mix and match all of these. So it's very flexible, but you give up some introspection. OK, and so as an interesting side note, the structural combinators tend to be linear. So identity, first, second, compose, well, not compose, pair, copy. They're all actually linear functions when they're implemented up here. So actually, you can reuse the same implementation, and that is also it's a subcategory of the computable function category. OK, and so a good reason to bring these two up that brings us to an interesting topic is automatic differentiation as a category. And actually, last week, Conal Elliott gave a talk at the category theory seminar at MIT. And it's an absolutely phenomenal talk. It kind of makes it almost pointless for me to talk. You should go watch it. But I think I have some things to say that maybe are a little simpler that hopefully will help. But there's a lot of really good insight in here. It's a really great talk. OK, so how do you implement automatic differentiation as a category? Well, basically, you need to bundle together nonlinear functions with their Jacobians. The Jacobian is the matrix of derivatives of a function, and I think it's really important to note that you really should be thinking of n-dimensional function to m-dimensional functions. You shouldn't work in single-dimensional variable calculus, and you shouldn't work with like a high-dimensional to a scalar function, because those build the wrong intuitions. And they're, of course, a subcase of the case in which you're just going from arbitrary, 10-dimensional function going to a 3-dimensional function. So in general, with a nonlinear function, there's a matrix of derivatives. The derivative should be thought of as a matrix. And actually, the chain rule from this perspective is very simple. It's actually, when you compose two nonlinear functions, you just matrix multiply their Jacobians. That's the chain rule. So the way we can implement automatic differentiation in category is we can just sort of bundle together the function category that I started with and the matrix category that I just talked about. And so the simple way you might do it is you just, you have a tuple of the function and the corresponding matrix that goes with it, and you just compose them in parallel. But that's actually not quite right, because when I said the chain rule is matrix multiplication, that is a slight simplification. Because when you actually look at the expression of the chain rule, there's this complicated dependence on the base point. So actually, what you need is the base point to actually be in scope when you're calculating the Jacobian. So actually, a better type is, or the correct type is this, because the Jacobian depends on where you're actually evaluating the function. If you have x squared or something, the Jacobian will be big over here and small over here. So the matrix you need to output depends on it. But basically, this is automatic differentiation right here. You bundle together the nonlinear function with the linear map that takes little displacements in the domain to little displacements in the codomain. And there you go. And so here is a style of doing it with explicit matrices. So the identity morphism takes XX, and then it's the identity matrix of the same size as the linear map. Composition looks a little more interesting. You need to evaluate the nonlinear function at x to get y, and then you have a Jacobian here. And then you need to evaluate the next function at y to get z, and then you have a Jacobian there. And then you need to return the total result, which is z, and then the composition of these two Jacobians, the matrix multiplication of those two Jacobians. And then you have domains. There's more structural combinators and domain-specific combinators that actually implement specific stuff, like sine and cosine. Those are sort of domain-specific things. And if this, oh, I haven't loaded in this one. Anyway, this does work when I have everything properly loaded. And yeah, the composition x to the fourth, 4 times x cubed is the derivative. OK, so then that's interesting and hopefully straightforward-ish. But there's some more interesting things we can do here. We can replace this explicit matrix representation with the functional representation of linear maps that I was talking about up here. And that gives you a road into doing reverse mode automatic differentiation. So composition is associative. But actually, the amount of work you're doing in these matrix multiplications depends on the association you used to do the composition. And there's good associations and there's bad associations. Basically, you want to do, if you have like a bunch of dimensionality that's changing, You have like a bunch of big dimensional vectors happening over here, and maybe they're sort of filtering down into smaller and smaller dimensional spaces into a scalar, let's say. You actually want to start the composition over at the small part and work your way up to the big part. There is a different asymptotic complexity to the different associations of doing it. So you'd want the thing to be associated the good way by default. And there's a trick to doing this, which in the functional programming community is sometimes called Hughes lists, and is related to the Cayley representation of a group and the Unay lemma, which is interesting. And basically, that there's a similar issue when you're doing list appending. When you want to append two linked lists, you need to traverse the entire first list in order to put it onto the second list. So if you're appending a bunch of lists and you associate it in the bad way, you can actually, it can cost n squared complexity in the length of the things you're appending to do the append. But if you do it the right way, it's linear. And so the way you can do this is by partially applying the append operator in the correct direction, in the direction you sort of want it to go. And that gives you a representation of lists called Hughes lists. And likewise, we can do the same thing here, where we can, we really want, in the case of a large dimensionality going down to a small dimensionality, we want to start at the small dimensionality, which is the end of the composition, which makes it feel a little strange and unnatural. But you can set up the matrix multiplication, and in some sense, such that it is associated to the at the end. And when you do this, that's what you get reverse mode automatic differentiation. And the structure of the combinator actually takes the structure of a lens. It looks identical to a lens that you find in the Haskell community. So here is an example of what that looks like. Identity looks like identity. Compose first, second. This is very similar to what I showed before. Yeah, other combinators. OK, so that is a model of how you can do reverse mode automatic, or what is reverse mode automatic differentiation. So ultimately, it's interesting to note how exotic is this perspective. I've ultimately decided it's not very exotic from the appropriate perspective. So there's a typical description of how reverse mode automatic differentiation is implemented is you talk about Wenger tapes, or you talk about building a computation graph and then traversing back through the computation graph. And there's some fairly standard functional programming tricks that I think basically convert this form of thinking about it into something that looks like those forms of thinking about it. So if you use a technique called defunctionalization, you can convert this closure into a data structure. And basically, that data structure is the equivalent of a Wenger tape. Also, if you closure convert to the existential lens form, so there's this other form of a lens that isn't something outputting a result and then a tuple of sort of had of a backwards pass. There's this alternate form which outputs this sort of state you want to keep around, and then when you're eventually ready to go backwards, do a backwards pass, you resupply that state. In a sense, that is closure conversion, where this is sort of the state that was tucked away inside this closure, because this function retains memory about x is sort of what its point. And on top of that, once you're in this existential form, there's another set of tricks that can relate data types with existentials in them to sort of object-oriented style. So this is very similar to that graph style when it's implemented using object-oriented programming, in that this is sort of the object parameter that's going into the backwards pass, and then it's receiving differential bits from the front. So the strict interpretation of what a lens in is Haskell is the thing that breaks apart data types and puts them back up. They're functional getters and setters. But this perspective shows that lenses actually can live on sort of a spectrum of control flow techniques. They're a way of organizing when you know you want to have a forward pass that goes all the way to the end, and then a backwards pass that comes all the way back, which is a ubiquitous control flow. This is a way of organizing it. But you could also organize it using continuations and coroutines, do very similar things. I'll just mention briefly, dual numbers is another way of talking about automatic differentiation. And from a certain perspective, it's a little bit wrong. You can actually convert anything in this form, this forward mode lensy style, into a function that looks like this, but you can't go the other way. And that's because correctly implemented automatic differentiation, this y parameter should never depend on this dx parameter. The actual nonlinear output shouldn't depend on the small displacement that you're putting in. So this type is a little bit wrong in the sense that it allows things that you don't want to happen. You never should have y depend on dx in a correct automatic differentiation implementation. Is this actually competitive? I'm not actually sure. I know high performance computing is a complex topic, and people have put so much work into reverse mode automatic differentiation frameworks that I don't even know what it would take to compare this style of doing things to one of the other styles. But there is someone working on something very related to this. Keno Fisher has been making the rounds with a preprint, and I believe he's giving a talk in a couple of weeks about sort of what his thinking is here. And he's very deep into actual implementations of things. So I would trust him. I would trust his opinion. I'm excited to hear more about that. Here's a blog post. Here's Cohn Elliott's Essence of Automatic Differentiation, which is the inspiration of a lot of this stuff. All right, so I'm going to move on to something a little bit different. Now I'm going to talk about relations. So we've been talking about basically functions before, but relations are also a category and kind of a more interesting one to me in many respects. Relations, one perspective of what a relation is it's an extension of functions. Functions are a particular kind of relation where you've constrained yourself that you need to define an output for every input, and there's only one output for every input. That's what a function is. But a relation allows you to talk about partial functions, allows you to talk about multi-valued functions. So it's sort of a richer domain. It also has, functions have a very unidirectional character to them, but relations sort of have this more bidirectional feel, which can be really useful for modeling things. Not everything feels unidirectional. In fact, a lot of the physical world isn't unidirectional. Things are just connected and they influence each other backwards and forwards is a pretty common way things are arranged. So here's a really simple-minded implementation of finite relations that I like because it's just so simple and it looks beautiful using comprehension notation. So list comprehension, set comprehension notation, something that Julia offers. Also Haskell and Python have this. And really I think it makes it very clear to read. So objects are finite sets, and then I can represent relations basically by arrays of tuples where the first tuple is sort of a piece from the domain, and the second part of this tuple is a piece from the codomain. So if you're going from a set M, and what's the identity relation? Well, it's for every x in M, it's a tuple of x and x. And then you can talk about composition of relations, which is an extension. It's a natural generalization of composition of functions, if you think about it the right way. And likewise, you can make first and copy and so on the structural combinators. Now, something that's really interesting that doesn't make sense in functions is there's a notion of a converse, which is the analog of the inverse of a function. But you can't always count on the inverse of a function to exist, whereas you can always count on the converse of a relation to exist. And then there's some other relations form a lattice. You have basically intersection and union operations on them, and you can talk about subrelations, a relation being a subrelation of another relation. And all of this hypothetically actually runs. It'll actually compute things. But of course, this is a very simplistic representation. There is a wide spectrum of other representations you might choose for this. In some sense, finite relations is the domain of databases, and studying how to efficiently store databases or query databases, like how to actually execute queries on them, is a big topic and a complicated topic with a lot to do. So there's a bunch of different representations you could possibly do that that are interesting. Just if you're interested in working with relations, just a note I want to make that very often people have already thought a lot about set representations. So basically, this is representing a set as an array of things. And then you can lift it up to, you can lift a set representation up to a relation representation. Now, I think there's wider classes of relation representations than just ones that are lifted like this, but it often gives you a very fast way to get something relational and executable. It's just by taking an already existing set representation. And here's some, I talked about this being a lattice. It can be interesting to think about subcategories of relations where you don't deal with intersection or union precisely for computational reasons. And some interesting lattices to work with are intervals, octagons, polyhedra, convex sets, terms with patterns in them, which describe sort of a set of terms where the pattern can get instantiated with different things, or linear subspaces. And here's a bunch of references. A really interesting book on relational mathematics is this book by Günter Schmidt. Here's an interesting sub-project under the algebraic Julia banner. Pixel arrays is an interesting idea coming out from David Spivak. So this is actually, it's interesting that relations are very similar to the linear maps I was discussing before. You can think of them as sort of Boolean valued matrices. And what I've done here is the analog of a sparse representation of a matrix, where I'm only listing the non-zero elements of that matrix. But you could explicitly use Boolean matrices as a representation, and you can do interesting things with that. So that's sort of what that paper is about. Here I describe this finite relation thing in much greater depth than I've done here. Some more interesting things on relation algebra, and yeah, interesting references. But all right, so here's the #1 thing I actually wanted to talk about today, and I have left myself enough time, and that's linear relations. So the importance of linear maps cannot be overstated. Like, they're the most useful concept in all of mathematics, maybe the most useful concept for engineering, for science. Matrices and linear algebra are the substructure upon which all scientific computation is built, basically. So they're kind of a big deal. But a linear relation is really, I feel, almost as good, as powerful a concept as a linear map. I don't want to be so, I don't want to have so much hubris to say it's as important, but because I can't possibly have that much hubris, but it's a really important concept, I think, that really has a really useful way of modeling things. So some examples of things that I think are well characterized by linear relations are control systems, linear control systems, circuits, discretized linear PDs and ODs, quadratic optimization problems. All of these things are better modeled as linear relations than they are as linear maps. Okay, so how do you actually, what is a linear relation? A linear relation is, it's a subspace of a vector space. A linear relation is, you have some output variables, and you have some input variables, and you have a linear relation between all of them. You just have some equations, sort of around. And you can implement this. You can just store those linear equations as matrices. So here I have a struct that I'm storing the linear relation. It has a left piece and a right piece. So that's storing the matrix. Every row of the matrix is a equation relating the inputs and the outputs. And I'm storing the piece of the equation that's related to the input in the left part, and the piece of the equation that's related to the outputs in the right part. Okay. So here, for example, the identity relationship would be an identity matrix and the negative identity matrix stacked next to each other. So that would say that this variable is exactly the negative of this variable. This minus this has to equal 0, and so on all the way down the diagonals. And you can compose linear relations. And basically what that requires is a projection process. When you're composing two relations, you have a set of variables it's meeting on in the middle, and you want to project those ones out and then see what sort of equations are left behind when you sort of solve those middle ones out. And that can be achieved. There's a null. The way that is achieved is when you want to represent a linear subspace, there's at least two big representations you want to talk about. You want to talk about a relation representation and a generator representation. So you can list it as a subspace is the span of some set of vectors, or it's the set of vectors that gets mapped to 0 under a linear map going to the scalar 0. Another way of talking about this in a more matrixy language is you can represent them as either a range or a null space. And you can use numerical methods to convert between these two representations. So it turns out that projecting is easy in the generator representation, but combining constraints is easy in the range or the relation representation, the equation representation. And so that's what compose basically does. It takes the two, it stacks them together into the combined constraint matrix. So combined constraints in the equation representation and the null space representation of a vector space, you just need to stack the matrices. And then you explicitly get the null space, which converts it to a generator representation. And then you can project, once you're in the generator representation, by just excising the pieces you don't care about in the generators. And then to close the loop, you convert back to the equation representation. Yeah, so this all actually can compute. And so things you can describe with that are circuit diagrams and control structures, control and feedback loops. And I have some blog posts where I go into this into greater depth. Here I talk about using circuits and how circuits are actually the circuit is actually a string diagram for these linear relations, which is pretty cool, like the circuit diagram. And here's a way of mapping. Lqr control is a particular style of specifying control using the tools of linear algebra. And what you can do is you can phrase it as an optimization problem. You take the gradients of a quadratic optimization problem, and you get linear relations out of it. And so you can build a sort of a compositional Lqr controller out of linear relations using those techniques. And that's what I was showing here in this little diagram. And an extension that this implementation doesn't do is sometimes you want, if you have time-dependent circuits, usually use phasor analysis, where the coefficients that are going into these linear relations are actually polynomials of the frequency you care about. So you need to go into sort of a different field of mathematics. I think you need to use modules as the appropriate place to work on that. And there's an analogous way of achieving composition, computing composition using module computations. And I discussed that a bit in that one. OK, so at the last bit of time, I guess I'll skip that. I want to talk about there's a technique that I've noticed that's really useful that could really quickly get you to a categorical DSL that actually does stuff. And there's the cookbook recipe is that there's many DSLs already out there that already compute things that expose variables. You can call a function that gives you a fresh variable. And you can, when something has that, it's very, I found it commonly possible to convert it to categorical combinators where you don't have to explicitly rearrange the variables. And so some libraries that expose things like this include JUMP, which is the Julia Mathematical Optimization DSL, CVXPy, which is a similar one. These are for solving linear programs or other mathematical programs. Z3 also exposes an API that's very similar to this. SymPy, Homotomy Continuation.jl seems to expose an API similar to this. And here is basically the recipe. So for every combinator, you make either a thunk or you carry some environmental piece that you're going to need. And then inside the body of that thunk, you call this function that creates variables. You create input and output variables. You also create new side stuff, usually constraints that you want to be built. And then you output from that function a tuple of those input-output variables plus the side stuff you generated. If you like monads, this is kind of a writer or state monad, depending on what you need to do. It's a state monad of the constraints, or yeah, it's a writer monad of the constraints, and sometimes a state monad on some environment that you're carrying around. So here is sort of an example of how this would look for JUMP. So you can think of an optimization problem as a category that's sort of combine, again, kind of like automatic differentiation was bundling linear maps and nonlinear functions. You can bundle together relations, which is a feasibility problem. You can with an additive objective function, and that gives you another category you can talk about. So that's a way of talking about optimization problems as a category. So you can make some combinators here. For example, the identity morphism takes in a model, just because this is what you have to do when you're using JUMP. Is you need to use this model and carry around and build variables that know they belong to this model. So you need to hand that in. And then you make a new variable that's of the appropriate size. And then you output the input variables, which is x, the output variables, which is also x because it's supposed to be an identity morphism, and then 0, which is the objective function here, because it's supposed to be something that really doesn't change the objective function. Composition can be achieved fairly straightforwardly. You call the first morphism, you call the second morphism, and then which each output, they're storing, in this case, the constraints in the model itself. And they are outputting objective functions individually. So then you add in a new constraint that the input of the second morphism has to equal the input of the output of the first morphism. You add that constraint, and then you add the objective functions, and that's how you can have compose. And then you can also implement O times, and you can eventually run. That once you've built up the whole thing you want to talk about, you can throw that thing into a run function, run the whole thing, tag the objective function actually onto the model, and then actually solve it. And again, you can see more examples of basically this style in these blog posts, where I do a similar thing for Z3. I do a similar thing in CVXPy. You can also do a similar thing to sort of categorically combine graphs, because you can ask for a new node, and that's sort of like creating a new variable. So that was a whirlwind and basically wanted to talk about. And I guess it's getting really late. So let's see if there's any questions. Yeah, thanks.
Thanks. Clap, 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 clap.
Clap, clap, clap.
Yeah.
Yeah, that was, maybe I should have tried to talk about less. That's what I'm realizing.
Okay.
Felt sort of rushed. But yeah, there it is. And there's, of course, I put in lots of references if you're interested in any of that. No questions? Or thoughts or comments or things you think that I did stupid? Or...
I'm trying to form a comment about this last thing, this optimization model. I guess I haven't read the relevant blog posts about that, but it looks quite similar. It actually looks potentially very similar to something I was trying to do, which I basically abandoned after I realized that argmax wasn't functorial.
Well, I'm not. I mean, I'm not bringing functors into anything.
Yeah.
It just is. I think at least, I can always be wrong, but I think this is a category.
I at least had the same idea of composing objective functions by addition, so the identity is the zero objective function.
It's not an unknown concept. In fact, it's extremely natural to do this. This is actually why I'm fairly confident about this, because let's say in physics, there's a method known as steepest descent. But there's a bunch of things to say about this, but the method of steepest descent takes linear operators and converts them into an optimization problem. So when you're doing integrals, sometimes you only care about a particular, like the integral is dominated by a particular position. And so you actually need to find that particular position, and that can be phrased as an optimization problem. You need to find the place where basically the integrand is biggest. And that connection is one that you traverse to go from classical mechanics to quantum mechanics, and also from statistical mechanics to thermodynamics. In addition to that, the notion of convex operator, you can find, I guess I didn't put a link to this, but it's in a link in a blog post. There's this book, Convex Optimization by Rockefeller. There's this Bible of convex optimization. And in a chapter towards the end, he talks about these convex operators where, yeah, you do the arc, like you were saying, the maximization is a binding form. And just like summation is the binding form that achieves composition for matrix multiplication, or the existential binding form is the thing that achieves composition for relations, maximization is a binding form that achieves composition for this category. So I think it's natural from multiple perspectives.
Can you see, I guess I'll read out. Boyan, do you want to read this out, or do you not have a microphone? I guess I'll read out Boyan's question. Let's call this emerging picture the numerical ACT paradigm, or the Connell way. Yeah, that sounds good.
Sure.
Have you encountered any fundamental limitations yet, i.e. numerical problems or methods that you can't treat this way?
I mean, that's a very wide, that seems like a wide question. Are there any numerical methods that can't be put into this format? I mean, are we talking about specifically this thing I talked about at the very end of like turning, there's a cookbook of sort of turning DSLs into combinators? Is this in Zoom that these chats are happening?
This is in the Zoom chat, yeah.
Can you hear me now?
Yeah.
Yes, I can hear you.
So completely agreed. But my question was, have you encountered any limitations? Like, is there something that you tried to do that you thought would work, but then didn't work in formulating numerical problems?
There's plenty of things that I thought would work and didn't work. Maybe that would be a good talk in and of itself.
Have you encountered any pattern of why they don't work?
I think the pattern that I'm most familiar with is that assuming everything is a lens and then finding out it just doesn't work out. I think that's the #1 pattern. Also, a pattern is these categorical combinators tend to hide stuff, and then you need access to these inner things later, or to actually do anything useful, you'd kind of want to see them. So that's another pattern that I've noticed. For example, here, mention just at the very end, the Iterative Lqr Controller. It's a way of taking an Lqr controller and applying it to a nonlinear system. And I was like, this is so obviously a lens. That was like one of the earliest lenses I was thinking about. And then because I was working in Haskell, which doesn't give me enough, Haskell makes you want to do things right, kind of. Like you don't want to just have some side effects that just get stuff done. You have to like know where your ST monad went or whatever. Like I couldn't just tuck things away in a way that would just like make it work anyway. But anyway, the problem with the Iterative Lqr controller is that really you need to save all the internal information and maintain it. It needs to be an algorithm that runs like iteratively again and again and again. It needs to save this previous passes. So it's not, strictly speaking, a lens without either having some storage or stretching what you mean by lens. Yeah, so I think that is a wide class of things that hasn't worked out, is things that I thought were lenses and weren't. Or just like the most simplest form of lens. What was that?
Isn't it a monad instead of a lens?
Well, I was saying, I think you need a lens that has some monad stuff sprinkled into it in order to actually get it to do what you need to do. But I don't exactly know how to do that.
There are
perhaps
papers about this, sticking a monad into lenses.
Is perhaps the generalization something along the lines of multiple forward and backward passes until some notion of convergence is achieved?
Yeah, I think that's another way of doing it. That makes a lot of sense. So you could sprinkle a monad in, or instead of having a lens that has a single forward pass, you could have a lens that has arbitrarily many passes. That's also possible to do, basically by turning it into a recursive type. Instead of it returning like a result, so there's the backwards pass returns the result, but then it would also have to return basically something that's the entire lens type again. And then it would have enough storage to like sort of remember enough stuff. And then again, that's part of the eye-opening that a lens is on the spectrum of coroutines and continuations and stream processors. Like that type is hard-pressed to call that a lens anymore. It's actually really, really similar to what you might call an iterate or a coroutine in Haskell. So, yeah.
But isn't that the continuation monad?
I mean, if you're willing to bring continuations into it, anything becomes possible. I think the interesting, you can implement the lens pattern using continuations, but the interesting thing is that maybe it's a more constrained world. Like the continuation is the go-to of functional programming, right? That's what people say. And so it's interesting to have understand the striations of power you need. Related to that, something I've been thinking about lately that I didn't talk about, I have no idea what to say about this, but continuations are interesting from a implementation perspective. Like, how do you actually implement a continuation? Well, there's interesting things at the low level going on with stacks. So I've kind of been wondering about, what if a lens was a primitive of the language? What do you get to do? Is there some like really optimal way of implementing a lens? And it kind of seems like there could be, to me. I don't know. Because a lens, another thing that's interesting is that a lens is almost function calls. Has anybody else ever thought about that? That it's almost parameterized function calls? Like when you have a function that's going to call another function forward in the chain, like you could make that function a parameter. It'll call this function next in the chain, but then that function will return, and then you can do something else with that result. And so at a high level, that's the same. At a high level, that is kind of what a lens is control flow. It's like something that goes forward and does a single pass backwards. The stack, like a regular function call mechanism, implements a forward backwards pass. But I've tried doing this a little bit, and they actually are slightly different types. But so you can actually convert any lens into that form, but you can't convert that form into any lens. So there's something missing there that I don't understand. I don't really understand what the difference is.
What you just described is very similar to the way one thinks about Bayesian models when one implements Bayesian inference, because you have the likelihood function, which is mapping from the latent space to observation space. And then when you do inference, you're in some sense inverting the likelihood function, right? And then that changes your belief over the latent space.
Well, yeah, that sounds right. That sounds right. It just, all these things seem vaguely related. I don't have a crisp picture of like, I'm pretty sure that a lens and a parameterized function call, a parameterized function call being a function that takes in the next function it's going to call and calls it, and then that returns and it does something a little bit more. That thing is still open in some sense. It's still an open object that you can like put stuff in on the other side, and it has a forward backwards pass, but it is different from a lens, and I don't really understand the difference of what you get or what you're missing. But this is something I was thinking about while I was writing this talk, so this isn't particularly digested ideas.
Can they be distinguished by whether or not they're tail recursive?
Maybe, I don't know.
Okay, we should probably stop because we're already overrun.
Yep.
Unless there's really burning questions still.
Of course, I'll be on Slack, not Slack, Zulip. And thanks for letting me talk. It was fun.
Thanks very much for an excellent talk. It's very enjoyable. Thank you.
Yeah.
All right, thank you.
Thank you.